what I've been doing. Some of you maybe know something what I have done. Other people don't know. So I'll show some recent results and some not so recent results. And before showing results, I think it's good to give some I put here like the general scheme of what I'm going to talk, but it's actually the general question I'm asking, the general hypothesis I'm exploring, if you want. You can see this like a computational exercise. What I'm trying to explore is the possibility that we can get sufficient information for atomic barrios from single sequences, and this information would be large enough to encode tertiary structures. So the question is, if we have a single sequence, we know that somehow it encodes a three-dimensional structure. What I'm exploring is the possibility that if this problem, or this encoding problem, could be divided in two parts, the sequences would encode like some intermediate informational step, if you want. In this case, I will explore atomic barrios being quantified by central distances, and this information would be sufficient for 3D structure determination. So, for example, we know that from many studies with Go models or structure-based models, if it's not hard to get some kind of information that it's sufficient to go to 3D structure, like contact information or dihedral information or a combination of both. We can go from here to here, if this were some kind of information. But this would be hard to get from here because it's a lot of information. So the general idea is to try to get something that it's sufficiently informative to get from here to here, but at the same time, the information is sufficiently small to be hopefully encoded in sequences. So this is the idea that we are trying to explore. So this would be a candidate for this atomic barrier. So if this happens to be the case, then the strings constructed from a finite alphabet of atomic barriers could then be regarded as a language, and maybe this could be useful if we do this, because so we could understand the constraints on this language or the grammar of the language, and this could provide a possible approach for barrier prediction from sequence, so to get from here, if you understand what's this. And then if this can from here to here, so it would be a possible approach for coming from here to here. And of course, this would be like an approach for structural determination from sequence. As it has been argued yesterday, maybe this, if you call it prediction problem itself, maybe it's not, even if you can get reliably native structures from sequence, maybe as a practical tool, maybe this is not that relevant or less relevant than it was imagined before, because we have now we have lots of other sorts of information, like templates, lots of templates, sequence alignments, and things like that. But even though if you can do that, get it really from a single sequence, so I think more important is that we have some much insight on the folding scheme. So it would be like an understanding. So I think this part is not, we don't understand the folding scheme, and I think it's still an interesting problem in itself. So most of my talk, I'll show results to try to show you that this possibility is not completely absurd. So it might be, it cannot be ruled out for now. Yeah. So I'll begin with a simple introduction. Then I'll talk about, in this introduction, because I noticed yesterday when Paul was giving his talk that there was some discussion about what we could do with lattice models and things like that. So in the introduction now, you show you some I made this yesterday after dinner. I will show you some old results with lattice models that are similar, or like, it could be like a motivation for what I'm doing now with off-lattice models. So I will talk about native Barrios. So this would be like, it would be very similar to structure-based models, but instead of giving the information about contacts and dihedrals, I will give information about Barrios. And I'll see if you can get to the native structure only knowing the Barrios. But it's native-like, it's native-based in the sense that the Barrios come from the native structure. So I'm giving information about the native structure, but not much information. That's the point. Then I would talk, I want to know, okay, if you can fold with native Barrios, but how hard would it be to get that from sequence? Because I would never be able to predict native Barrios perfectly from sequence. So I will try to estimate how accurate the Barrios has to be. So I will try to, I will make show simulations where I, on purpose, erase some of the Barrios, like or scramble some of the Barrios, and see how much scrambling or how much erasing I can have and still have folding to the correct structure. And then I'll show some simulations using predicted Barrios. So this actually from sequence trying to predict Barrios. And you see that this we can do but only for a small fraction of sequences for now. The sequences that are better predicted than average. So we probably, this is the point that if we want to go on with this, become this more general, we have to be better on this part, how to get the Barrios from sequence. And then if we see this Barrios as a language, maybe, as I said before, understanding a little bit of this language being this set of sequences of Barrios that represent structures, we could do a better job on predicting Barrios from sequence and then structure from sequence. That's the general scheme. So so this I put here yesterday because of this discussion about lattice models. So I think this is an interesting old result I have from I think this is 99. It's pretty old. So it's almost 20 years now. Wow. So I was asking a very similar question. I want to know, in the context of a lattice model, can an unspecific hydrophobic potential, something of this simple as this, the energy of each conformation would be the sum over all beads. This number here is the number of contacts the bead is making, so it's conformation dependent. And this number here is the hydrophobicity, that we call hydrophobicity of the bead. So this is the sequence dependent. So in this energy function, each conformation enters the energy as this contact vector, and the sequence as the hydrophobicity vector. So essentially what we are doing here, that we are trying to say to each bead, not the partner in contact they want to make, like in a Go contact model. We are trying to say how many contacts it wants to make. And this is less information than the contact partners. So I say that maybe we could fold in the lattice, not trying to tell each bead who will be, who likes whom, but how many contacts each bead wants to make. So this is a smaller amount of information. And at this time, it was not very clear that this could be possible. What people were doing to fold lattice models, or they could use contact go potential, so only native contacts would be favorable, or they could try to select sequences with many letters with a contact potential, so the sequence in a given chosen conformation will have a deep energy minimum. And to get this deep energy minimum, I think Jose told us yesterday, this would be like a criterion for protein-like folding behavior. So if you have a simple model and you can get any kind of potential that generates this deep energy minimum, so the energy of the native conformation is much smaller than the folded state, so you could have folding behavior. So the hard part is to get this, to get potentials that have this property. So in the Go potential, you do this, just telling who wants to make contacts with whom. So what I'll show here is that we can maybe do this, at least we can do this in the lattice, with a simpler energy function. So we don't have to tell the, who is making contact to whom, but just how many contacts each monomer wants to make. Okay. So what I did here, so I began with this function. I posed this. I want the function to be like that. And I use this criterion of the z-score criterion, if you want. And what I found is that maybe this could be a larger chance of being a good, provide protein-like folding behavior. But there would if you have a property on the contact vectors, that is a property of the structure, that would be more likely to be folded by this potential. And people this time try to fold only for maximally compact conformations, because people say, oh, proteins are more or less compact. So in the lattice, maximally compact conformations would be a reasonable choice for native structures. So it is not for this potential. For this potential, native maximally compact conformations are not good structures. So I just want to stress that this potential is very simple, and contact formation isn't specific. It's just favorable for hydrophobic, age plus larger than 0, and then favorable for hydrophilic, age smaller than 0. I'm not fixing here how many letters I have. Okay, but the age is larger than 0, this will decrease the energies. Age is less than 0, we increase the energy when we form contacts. So it's simple. So so can we do reproduce protein-like behavior with this in the lattice? And so the answer is yes. But native structure. And this is why people are not being able to fold proteins in the lattice with this certain specific potential. They needed contact-specific information. So, and segregation is quantified by the standard deviation of contact numbers from their mean. So this is like a segregated structure. It means that you don't have like those cubes and regular solids as a native structure, but you have things that you have many monomers making no contacts at all, the white ones, and you have many contacts making lots of contacts, the dark ones. And the number of letters to fold this is actually small. It's like 5 letters, because each color corresponds to the number of contacts and also to the, in the model, to the hydrophobicity. So things that make more contacts than average are hydrophobic, are dark, less contacts than average white. So these things in Monte Carlo, they fold, well, it's protein-like in the sense that this is for residues, I think. So this is too large for complete enumeration, but with this simple potential, I can have well, I show you long trajectories that the chain, this is the energy, so the energy jumps abruptly from high energy to lower energy, and jumps like that. And when I go to the lowest energy, I always get the largest number of native contacts, and I never can get other conformations, non-native conformations with energy lower than the native. So, and it's reasonably abrupt, and so it seems to be possible to fold this unspecific potential. So here, if you are hydrophobic, it doesn't matter where you are. You want to make contacts, so you don't know who your partners should be. And so, and then, and since we can do this with a small number of letters, it is implying that I'm using a smaller amount of sequence information to do that. Okay. So that's okay. So this is pretty old. It's 99, 21, 2001. So now something more interesting. What do we know for off-lattice models? And the talk today would be mainly about these off-lattice models, what we know about this. So, what we know is that first, At least we guess this is probably right. That native burial information, that is central distances, is sufficient for structural determination. So we have a few papers on that. So if we know I will be more clear what native burial is, but what I'm saying, if I know this, if I give the information about the central distance of each atom in a protein, I can get to the native structure. And the burial information, this is some estimates we have. It's not so large, so it could be maybe it's not on our estimates. It could be close to 4 bits per residue, or a little bit less than that. The sufficient information for structural determination, and this could be entropically compatible with sequence. So that's what we. But and then we also have. So this would be other. That now we are trying to get sufficient burial information, actually obtainable from sequence. So we are showing that some prediction to this what we call the hidden Markov model, some machine learning approach to get burials from sequence. We can get sufficient information for some proteins, but not for all. And finally, doing our estimates of how accurate or how much information we need and how good our predictions are now, we'll try to, we conclude that probably more information, possibly beyond the capabilities of an HMM, should be extracted from sequence for most proteins. So this is what I'm going to talk to you. So we begin with native burials. So here, this is actually, Paul was was telling us yesterday about his structure-based models and his owl atom structure-based model, alpha structure-based model. So what I'm showing here is could be owl atom models, and they are adapted from the program developed by Paul himself for simulating owl atom structure-based models. But since I want to check if you can get only with burial information to get to the native structure, so I put this in this, I plug in this native or eventually sequence-dependent burial potential that will simply push each atom towards its native or predicted burial layer, and we have a small number of burial layers. So we can think like we divide the protein line if it was like an onion or something like that, with a small number of layers, and I tell each atom which layer it wants to go, and this number is L. And so I push the atoms to these layers. And we also need, of course, because I want to see if you can fold only with burials, I have to remove native-dependent terms and contacts and unrigid dihedrals that are in the structure-dependent code. And it's very important that if we only put burial information, we cannot get to the native structure. But if we put on top of that sequence-independent term reinforcing hydrogen bond formation, then we can get to the native structure. And this is important because we have to be okay. We need a small amount of sequence information because we have sufficiently high amount of sequence-independent information, the restrictions provided by hydrogen bond formation and things like that. This would be similar in the lattice case of the restrictions of the lattice. So the chain enabled to be encoded a small amount of information from sequence, it has to be sufficiently restricted by non-sequence information. And in these simulations, this hydrogen bond term, it's a more technical problem, they would be annealed in the sense that they would begin very weak or zero, and then the term will increase during the simulations just to avoid kinetic trapping of forming early the hydrogen bonds before we get to the correct structure. So, so this is the scheme. So the protein is like reasonably globular. Of course, central distance will correlate with actual atomic burial for globular proteins, but not for other shapes. So if this the central distance is small, it will be buried. If the central distance is large, it will be exposed. So in this case here, I'm dividing this protein in 4 layers. And the division at this point was just to make the 4 layers equally populated. So one fourth of the atoms are here, the other here, the other here, and the other here. And that's why the ones here are thinner, because the spherical shell grows, get out of the center. So the potential I'm using is simple. Okay, that's okay. Okay. And then this is the potential I told you. So we have, in this case, 4 layers. So the atoms that are in the middle, the center, they feel this barrier potential here, that you have a 0 energy if they are where they should be, and a constant force pushing them if they are out of there. And you have this for each of the layers. And this thing here is the hydrogen bond requirement, that it says that if this is imposed on polar backbone atoms, if they are internalized, if they get close to the center, they must form a hydrogen bond. If they don't, they have this energy penalty here. But if they are outside, they can form or not form the hydrogen bond. So the hydrogen bond must be formed if they get close to the center. And this is sequence independent. And it's partner independent too. Okay, so we want to get to the correct layer, and if we go inside, we must form hydrogen bonds. That's it. So it's very simple. It is very simple. So this is how just how that potential is constructed. So yes, and this is the hydrogen bond term that I had to include to force. This is very important, that the hydrogen bond term is it doesn't depend only on the distance between possible donors and acceptors, but also on 2 angles. So it's a directional. There is a directional part. So it's this number here for each possible hydrogen bond is the product of 3 step functions that they go from 1 to 0 when the variables get larger than a certain threshold. So a distance, this I think is like 3 angstroms, and you have the 2 angles here. So the thing is that this is one when all things are satisfied at the same time. The 2 angles and the distance, and this is 0 when otherwise. And you can control how abrupt this is by choosing beta appropriately, and me will give you where you want the transition to be made. So it's a very simple idea. So this is how we define the distances, the distance between donor and acceptor. The angles are like here. So it will depend on 5 atoms. Each hydrogen bond will depend, which potential possible hydrogen bond will depend on 5 atoms. And on top of that, the energy is, if the hydrogen bond is formed, it can go anywhere. If it is not formed, we have a penalty if it gets near to the center. So that's the general idea. So this works. Well, I don't know. Let's see. So you have this would be folding trajectory for a very simple alpha protein, the ENH. So this is just two layers. So half of the atoms wants to go to the middle, and the other half wants to go outside. So we have 2 layers. And we begin our trajectory. Remember, the hydrogen bonds are annealed. So at the beginning, there's no hydrogen bonds, but the atoms already know where they want to go. So in this case, you can have large fluctuations. These are like 25 trajectories. Yeah, I think 25. They begin unfolded, and then you run your simulation, and you push at once all atoms towards the barrel, the layer they want to be, and then increase the hydrogen bond gradually. So in the beginning, you have large fluctuations on RMSD, but some of them can go smaller than 5, and then fluctuating like that. And as the hydrogen bond becomes stronger, they fluctuate less, and some of the trajectories end up here, far away from the native, and some of the trajectories end up right here, between 5 and 3 or something like that. So what happens if I begin from the native structure and with hydrogen bonds turned on from the beginning? So this is pretty much similar to what I'm seeing here at the end. So the thing is not stable in the native structure. It stays here for a while, but it goes up and down, goes up and down. Okay. So it means that for L equals 2, for this very simple protein, this is sufficient, I don't know, to get close to the native structure, but it's not stable there. Okay. So what about if we go to 3 layers and 4 layers? So 3 layers, the fraction that goes close to the native structure is larger. And if I begin with the native, it fluctuates a little bit, but it doesn't move out. So it becomes not only accessible, but also more stable. And with 4 layers, something like this. Okay. So I have these kinds of simulations for many proteins. So I want to summarize all the results of all these plots in a single graph, so it will be easier to analyze what we are seeing. So this, what I'll do, I'll take the last 10% of each trajectory, folding and unfolding trajectories, and then you take the average RMSD of this last 10%. And for example, this for 2 layers, if the unfolding trajectories, and this would be the average of this RMSD over the 25, the maximum, the minimum, and in the folding trajectories, I also color here the global, the energy minimum, the barrel energy minimum. So this would say, okay, if you didn't know the structure, what would be the minimal energy? Okay, so the one I would guess would be the structure. So if for 2 layers, as we saw, even if we begin in folding trajectories, some get near to the native, some get, but they fluctuate a lot, and the native is not distinguished from the other place, because the minimal energy is in the wrong place. And if you begin in unfolding simulation, it's not stable, they move out. Now if you begin with 3 layers, they are stable, so the unfolded doesn't go up, and they are accessible. It goes down, the folding simulation goes down, and it's distinguishable. The native structure is right here. So. And with 4 layers, it's even more accessible than that. But this is, okay. There is a little difference in average RMSD, but it means that for this protein, 3 layers, just 3 layers is pretty much sufficient to get the native state accessible and stable. That's what you're. So this is another small protein. Now you have alpha beta. This is 4 beta strands and a single alpha helix in the middle. And again, if you be 2 layers, it unfolds, it's not stable, and it doesn't get to the native structure. It's different from here. It's not accessible, it's not stable, it's not accessible, at least during this time, the simulation conditions. But with 3 layers, it becomes stable and more accessible. And with 4 layers too. So with 3 layers, I can fold this one and this one. And 3 layers, I think it's not a large amount of information. That's the point. So we are. Okay. This is a little bit more complex. So it's larger. But again, this alpha helix, and then we again doesn't fold. It's unstable, and with 3 layers, we begin to be more stable and accessible, undistinguishable. So 3 layers is also sufficient for this one, alpha helix. And this is like a more beta, small beta barrel. And they are stable maybe because of the beta barrel, but it's not accessible, it's not distinguishable with 2 layers. But with 3 layers, already distinguishable, accessible, and stable. So 3 layers for these very small proteins appears to be sufficient, and it doesn't depend on the structural class and things like that. It's because you can get beta proteins, alpha beta proteins. This is a little bit more larger protein. So here we needed more layers, at least in this condition. So it was not accessible with 3 layers. With 4 layers, it was getting there, but it it was not distinguishing. So, and we needed more trajectories. This is the plus here. And with 5 layers, we are able to get it stable, accessible, and distinguishable. And this is a little bit more complicated. And this is maybe the more complicated. This is an IG domain. They are like a complicated arrangement of beta strands going up and down. But even with this complicated thing, we can still have stability and accessibility and distinguishability with 4 layers. Okay, so it seems that knowing the Barrios, knowing the layers, it appears to be not much information, but it appears to be sufficient to get at least some low resolution but correct topology of the structure. This would be like between 3 and 4 angstroms, I think. We have to. Oh, it's right here. This one is like 4. This is 3. Okay. So so that's okay. So if you know the correct Barrios, we can get to the native structure. But we'll never be able to get, even if it's a small amount of information, we'll never be able to get perfect prediction of Barrios from sequence. So how much information I need, or in other words, how much wrong I can be and still get to the native structure. So this experiment, this computational experiment here, is similar to maybe you know about these experiments made by Shannon in the 50s, but to try to estimate the entropy of English text. So he gave like a text for somebody to read, erasing some letters, and the number, the fraction of letters the person was able to read, understand. So it was this would an indirect. Well, it was like a measurement of the redundancy of the language. Okay. So what I'm doing is erase letters or can scramble letters. Okay. So what I'm doing here, we begin with this 4 layers is sufficient for these 3 proteins here we showed before. So we run here unfolding simulations with the native, with the all Barrios on. So, and then we begin to erase the Barrios term of a fraction of the atoms, a random fraction of the atoms. I don't tell the Barrios, I don't tell them where they want to go. They just have to go to the middle, any one of the 4 layers. Okay. So if you can erase 50% of the, and it's still stable, it doesn't unfold. With 75%, like 3/4 of the atoms erased, it begins to move up here, become less stable. And here, instead of removing atoms, I'm scrambling atoms. But these fractions here are not exact because I need. It's harder to this. You can make this correspondence here, but it's harder to recognize the text if the letters are scrambled than if they are erased. So 50% erasing here corresponds to 50% redundancy, but this fraction here, 19%, would correspond also to 15% redundancy. That's what I'm saying. So if we scramble, we also can go to 0 redundancy. This would be 50% and 75%, and more than that, it begins to move up. And not only stability, but also accessibility. So with 0, it folded, we showed before. And with this 50% scrambling, or more or less, we can still more or less half of the times still be accessible. So here, so these are the 3 small proteins: the alpha, alpha beta, and the beta protein. And this is more or less similar to all of them. The only difference is that the beta one, it's having more troubles to be accessible with a smaller fraction of scrambling. And maybe this because we interpret this. Maybe it's a kinetic problem of the beta. We needed more time. It's hard to. It's not definitely what's going on here. So, but at least for these 2 proteins, what we estimate is that for 4 layers, we don't even have to know all the Barrios, just 25% of them, or a little bit less, because 75% is redundant. Okay? So this is interesting, because the higher this number, the worse can be my Barrio predictions from sequence. Okay? So how are my predictions from sequence? So I'll show you here. This is a plot. These are like this is like 300 small proteins. So we trained a hidden Markov model. This was adapted from a hidden Markov model to predict secondary structure, but instead of predicting secondary structure, it's predicting Barrios, atomic Barrios. And these numbers are like, so each point here corresponds to the prediction of a given sequence of these 300 sequences. And this is the inaccuracy. So the higher this number, the worse the prediction. So our worst predictions are 75% inaccurate. So this is like a random, because you have 4 layers. If you choose by random, each layer you have 25% right, 75% wrong. So these are very bad. These are just like random. These are the small inaccurate, so very accurate. So it's like this is 4. So it's like a little bit less than 6% right, this ones here. And this would be the prediction uncertainty that should be compared to the redundancy we estimated from our erasing simulations. It would be like 75%. So only a small fraction of our predictions, the best predictions, are actually below the 75% estimate we had. And these ones would never be able to be useful because they are like random. But we have a large fraction here, that corresponds to this one, that are above 75%, but still not random. So our idea is that maybe this could be improved or something like this. But just to show that this makes some sense, we choose 3 structures here that the predictions are good, and with the uncertainty less than 75%. And this would be sufficient if we did was more or less reasonable to get to the native structures. For these ones, we would not be able to get to native structures. So this is what I'm doing here. So we have the predictions in the discrete hidden Markov model. This was published before. The hidden states in the Markov model are a fragment of adjacent C alpha Barrios, and we have this. We need C beta orientations to get. We predict the C alpha Barrios, C beta orientation. So from that we can get estimates from all the atoms, because we need all the atoms, not only C alpha. Okay, but this is done. Those results are shown for all atoms for the quality of the predictions. So this we have. This is the transitions, emissions. So this is. So these are what's going on. So we have this. It's another way of showing what I showed before. We have this 200 and so almost 300 proteins. Some of them, the accuracy is very high. Some of them, the accuracy is terrible. And most of them are around here. What I'm saying is that these ones are sufficiently accurate to get to the native structure, if our estimates are right. And this is just to show that this range of accuracies or inaccuracies is not because we have some because the training what we do, we have all the proteins, we take one out, train on the other structures, and then we predict the one that is out. So what this is to show that the best prediction is not because we have something in the data bank in the training set that's more similar to it than the others, because this would be like the structure in the data bank that's most similar. The sequence in the data bank that's most similar to the native structure. So we removed everything above 25, but on top of that, there is no correlation between quality and the similarity to the data bank. Okay. So this would be the top, this would be the average. And there is no relation to structural class, beta, alpha, or things like that. So we don't know why some are better than others. That's what these are the 2 examples that were around here. so this is 4 layers. So red is the native. So we have just four levels because we have, this is the center of each layer. Okay, and these are, actually it's pretty good. It follows very well. So these are voting trajectories for the alpha protein. So this is now is predicted Barrios. This is not native Barrios. And some of them goes down. The others, not all of them go near the native structure. And this is the native. And on top of the native, we have the one that is with best burial energy. So it's not only, we don't not only get to the native structure with the predicted Barrios, but we can distinguish it, at least for that. So 3.6 angstroms is the RMSD of this structure. That is the best energy, and this is the best RMSD, but not the best energy. Okay. And we can get this to the other one, the alpha beta, the 3-fill, 56 residues. Again, the same thing. And this one is a little bit harder, but we can get to 5 or 6 angstroms. And this is the lowest energy. It's I think this around here. It's a little bit more than 5 angstroms, but it has the right topology. And it's funny that this thing here that is not supposed to be a helix, our hydrogen bond potential forced it to form a small helix here. But the topology is correct. So I think it's an interesting result. Just just summarize, this is what I'm doing, what we are doing, what I showed you, is that if you have the structure like this, we can encode this structure. We can tell about the structure. The distance from the center for each C-alpha atom, this is the trace here. And these are for all atoms, not only C-alpha. So we can see that why it's informative, because from how deep it goes, these things here, it's how close it gets to the center. So it can distinguish very easily, for example, the external beta from the central beta. This goes to the center because it gets closer to the center. This doesn't get as close, so it's like an adjacent one. This is the alpha pattern here, getting very close to the center. The other beta and the last beta, very close to the center. So this is what we are encoding in a discrete way. Okay. So you're saying, and if this is the sequence that, like protein sequences, we know that they encode the structure, but they look like random sequences. It's very hard to see patterns here. And so what you're saying that maybe this is not directly the language we have to look for, but maybe this would be like a code for a more language-like language, something that you have lots of correlations. So you have this way, because of the thickness of the layer, you cannot jump from 2 to 0. So you have 2, 1, 0, 0, 2, 1. This is this thing here. So you have highly correlated local correlations. This can be captured by the HMM. But you can also maybe have non-local correlations that could be captured by something more sophisticated, like context-free grammars or things like that, that could get maybe correlations similar to parentheses correlations. When every time you go in, you have to go out some time before. And this can be far away. For example, in the helix thing, you go in here, and you go out only here. Maybe this kind of non-local correlations could also be explored, but this is very preliminary. So this is the summary. So I think I showed you that native information appears to be sufficient for structural determination, at least for these small proteins up to 100. That it doesn't depend on the structural class. The amount of information appears not to be that large. Could be comparable or compatible with the entropy of sequence, so possibly could encode it in sequence. And we are able to actually get sufficient information for a small fraction of sequences with the HMM. But maybe more information, possibly beyond the capabilities of an HMM, should be extracted. We would have to go better than that for most sequences to be something reliable. So finally, I want to thank this more recent work was done by these two guys here, and Leandro is not in the lab anymore. He's actually in Rio Preto, and Juliana also left the lab. And some of these ideas were developed some years ago while I was working with José Onushik. At the time he was at San Diego. And some years later, before that, with Eugene at Harvard. Okay, thank you very much.